And I'm getting... You looking for your button? Okay. These blue ones are a little different, so I'm sure it's on here somewhere. I might just get you a different one. Let's go grab a different one. I need to find, oh, maybe it's math, but it's easier if you just have a button for it. So on the blue calculators, it's hard to find the natural log button, so you might want to avoid these bright blue calculators if you get mine over the next few days. Yeah.
Are we putting in the number of moles or the molarity?
Good question. So on this one, it's the same, so it doesn't matter. But in general, you're going to do it with the molarity. So I'm dealing with my red column right there. This one was just 1 liter, so it's the same number. But on other questions, go with the molarity. So it's the natural log of the concentration that we're going to be plotting. Yeah. First column, I divided moles over liters, and they told me it was a 1 liter vessel, so it turned out to be the same number. All right. If it had been done in a 0.5 liter vessel, I would have said 10 over 0.5, 6.7 over 0.5, and I would have had to divide by something other than 1, and the numbers would be different. All right, going on down here, we got 1.1 and 0.69 there. All right, so let's plot those again on our graph. Time axis is going to be just the same as it was before, so that makes life easy for us. 0, 40, 80, 120, and 160. And then on the other part of this graph, I counted 1, 2, 3, 4, 5. Every 5 squares, I've made it 1. That made it easy for me to fit everything in and find the values that I would plot. So I'll go 0 up 2.3 over 40 up 1.9 over 80 up 1.5 points plotted, get your straight edge out or ruler out. Or I mean, you can kind of eyeball it. If you're really insightful, you could probably even look at the table and see a regular rate of change on the table in the first place. And that's probably going to make a straight line for us. Because this one made a straight line, that means this reaction is first order with regard to A because it's following the first order rate law. The natural log graph is becoming a linear equation when plotted versus time. So I know that we can say rate equals K times A to the first power. If the first graph we made had been a straight line, this would have been my rate law, but since it was not a straight line, I was able to decide it's not 0 order with regard to A. This one does make a straight line, so that's looking good. Just to be sure, let's make sure that we didn't just get lucky and it looked like a straight line. You know, sometimes maybe it's just our graphing made it look like a straight line. We want to make sure that it's not second order. It can't be both, but just to cover all of our bases, kind of like in a multiple choice test. If you know the answer is B, but you just want to make sure it's not C, we should go ahead and plot this last one. Also, just to learn how to plot the last set. So, the last set we're going to look at, we are going to take, you don't have to use any special buttons on your calculator for the last set. For the last test, we want to find out, is 1 over A versus time going to give us a straight line? So I'm going to take all my numbers from column in red there, and I'm going to divide 1 over the concentration of A. I'll do 1 over 10. I'll do 1 over 6.7. I'll do 1 over 4.5. And I'll put those down as decimals so I think it's going to be easier to graph them if we write them down as decimal values. So maybe the hundredths place would work. So 1 over 10 is 0.1. Get 0.15. So I always do the operations on the concentration column. I'll hit the lights again. And then we're going to plot that last column as our Y column for the last set. Time's going to look the same on the x-axis. And then on this column, I'm counting every 2 squares up as 0.1 on this axis, I mean. Plot these points. 0, 0.1, 40.15, 80 was 0.22, 120 was 0.33. First it was looking pretty linear, but now it's starting to take off a little bit. If I can't really tell if it's linear or not, I would put a straight edge up next to it. And when I do that, I realize, oh, that's not as linear as the other one. Times A to the second power, where A is just any reactant. But since it's not a straight line, it's not following second order kinetics with regard to A. So what this turns out to be, it turns out to be a test to find out what order are we looking at. Only one of the 3 graphs will ever make a truly straight line. 2 of them look like they're straight lines, you might want to graph it again and make sure you hold a straight edge up next to it because we need to graph it again. Also, you can even see in the chart, only one of those columns between red, blue, and green, only one of them shows a regular rate of change. only the blue one changes by 0.4 every single time. The others, the change between each block, each pair of blocks is changing, so we know those can't be linear. They're going to be curved in some way. So you can even see it from the table much of the time, but the graph really proves it by showing that one of them is following a straight line. All right. If we flip the sheet over and go back to this chart in the second row, this is more important than the individual equation. The individual equations are why this works out. But here's what we're really looking at. When graphed, the straight line for natural log versus time tells us it's a first order reaction for that reactant. So that's why we ended up going with the power of 1 for this one. If the green graph on the screen, the 1 over concentration, that's called inverse of concentration versus time. If it gives us a straight line, then we know it's second order with regard to that reactant. We can get one more piece of information from this, which is the rate constant. So remember before, when we were looking at the homework from yesterday, we had to find the rate constant. There's a way to find the rate constant with this method as well. The rate constant is the slope of the straight line. Rate constants are always positive, so keep that in mind. Rate constants are always going to be positive numbers. So we need to find the slope of our blue graph. The slope of the blue graph is the value for the rate constant for this equation. How do you find the slope of a straight line? Yeah, find any 2 points and find their change in y and their change in run. While I'm thinking about it, let me go ahead and answer question A. It's first order for question A. First order because the natural log graph was a straight line. We say natural log graph is linear. And now to find the rate constant, I'll do it on the board and we'll put our answer on the sheet. The rate constant K is going to equal the slope of whichever one gives this straight line. Keep in mind, sometimes the graph, especially this graph, sometimes that one, but usually this one, gives us a negative slope. But rate constant, you just drop the negative sign. Rate constants can't be negative. So let's find the slope of this line. I'll go with the first point and the last point. So my first point on my blue graph is 0, 2.30. And then my last point was 160, 0.69. Slope is just going to be your change in y minus your change in x. So technically 0.69 minus 2.30 over 160 minus 0 to the other side of this. I'm going to get a negative slope, but I'm going to drop that negative sign because rate constants can't be negative numbers. Negative 1.61. Slope is negative 0.010. For my rate constant, I'm going to drop the negative sign. Put that back on the answer up here. So and then if it's first order, the unit for a rate constant for a first order reaction, we could go back to our chart from the end of class yesterday. It's actually just going to be seconds negative 1. So now we know two things. We know the rate law for this reaction is rate equals K times a to the first power. And we know that the value for K is 0.010 seconds negative 1. The last thing I want us to practice with is how to get a half-life. Okay, what half-life is how much time does it take for the reactant to be cut down to half of its original value. I can estimate it looking at my original data, but I want to find it specifically using an equation that's on the back of your handout. So this takes us back to some stuff from honors chemistry about half-life for radioactive things. You can apply half-life to kinetics for things that aren't radioactive as well. If you started off with 10 moles, what's half of 10 moles? 5 moles. We want to know, how long did it take to get from 10 moles to 5 moles? Well, it took about 80 seconds to get to 4.5 moles. So I know my half-life is going to be somewhere around maybe 70 seconds or so, right? To get to about, go to this first graph, to go from 10 to 5, looks like it took somewhere around 70, 75 seconds. But we want to find it using an exact equation. Flip your handout over, and there are two half-life equations on the chart. If a reaction is first order, the equation for half-life is T half equals, I think, is it 0.693 over K, or is it upside down? Yeah. Okay, that's on top. So, you know, K, you can find the half-life. Get this back on the main screen. And then because we were measuring all of this stuff with seconds, also because our rate constant was per second, we can estimate the half-life, actually we can know because we calculated it. The half-life of this reaction is 69 seconds, and that makes sense looking at our data as well. With first order reactions, it's really easy to find the half-life. If you know the rate constant, just do 0.693 over that, and boom, there's your half-life. That also means it would take another 69 seconds to go from about 5, again, the first graph is good, just looking at the changing concentration over time, to go from about 5 to 2.5 took about another 69 seconds. So remember, half-life is how much time it takes to go from wherever you are to half of that, and then to half of that, and half of that. So half-life isn't necessarily it is a regular time interval, but our first graph was not linear because it wasn't decreasing at the same rate all the time. The rate was slowing down, but half-life is how much time it takes to go from whatever you have to half of that. If it had happened to have been a second order reaction and the natural log graph has given us a straight line, if that had been the case, what equation would we have used to find half-life for second order reactions? Looks like it's a little more complicated, huh? 1 over K times, what does A sub 0 mean again? The initial concentration. So that's one thing that's interesting. First order reactions have a really simple half-life equation. All you need is the rate constant. Second order reactions, the initial concentration affects the half-life. So when you have a really high initial concentration, you have a big denominator again, remember? So they have a really short half-life at a high concentration initially. But as the initial concentration decreases, that extends their half-life out. So second order reactions are more complicated in that the half-life depends on their initial concentration, but first order it does not. All right, we've done all the work we need to do. This just reviews the stuff we talked about, okay? So this is just a little bit of a review right here. For first order processes, if a reaction is first order, the plot of natural log gave us a straight line, and the value of slope will be the rate constant. We just dropped the negative sign because rate constants are always considered to be positive numbers. This is the kind of steps we've gone through with other reactions with our example. You get your initial graph. It's typically curved like that. It could be pressure. It doesn't have to be concentration. And then, just like we did, they took the natural log of all their pressures, they graphed them, and they got a straight line. So they were able to prove that this reaction was first order, and then they found the slope, dropped the negative sign, and were able to get a rate constant there. Let's look at something if it's second order, since our example was just first order. If you had a reaction that was second order, you would have gone through the same steps we went through. There's our concentration data. There's the natural log data for a different reaction. This one is still curved. So if the natural log graph is still curved, you would expect to see that your last graph, so again, the plot is not a straight line, so it was not first order. But the final graph for this data, when they did 1 over concentration, that would be the graph I did in green. All right, this one gave a straight line, so you can get your rate constant from the slope of that line. Because this is a straight line, this particular reaction is second order for that reactant. All right, just as a reminder what half-life is, half-life is how long it takes to go from whatever you started with to half of that. So if they started with a pressure of 150 torr, it's how long it took to get to 75 torr. And then after that, from 75 to half of that, it's a regular time interval to go from whatever you have to half of that. And there's our equation. I do want you to put a little note on your chart here. For first order reactions, one important difference between first and second order. For first order reactions, the half-life does not depend on the concentration. So the half-life won't change even if you change the initial concentration. So A sub O, remember that's our initial concentration. And then also on that chart, we could just compare that. For second order processes, all the math in black is just how we get to that formula. This is the formula or the equation to focus on here. Half-life is 1 divided by the rate constant times the initial concentration. For second order processes, then the half-life does depend on A sub O. Since A sub O is the denominator, if you increase the initial concentration, it makes the half-life decrease. I'm going to get this out. This is your homework assignment. It's mostly about looking at graphs like we made. If it's a natural log graph, it's a straight line, first order. If it's a 1 over concentration graph, it's a straight line, second order. The lab that we do on Tuesday of next week, you will do a reaction and watch the polarity change over time, and you'll decide if it's first or second order based on what we did today. So we'll get some more stuff about these graphs next week as well. This is what the lab is based on. Take one of those and pass it back. This is your homework assignment for tonight, using that stuff we talked about today. Be sure you replace your calculators and your rulers on the way out for me today.